Hello everyone, welcome to physics. Today we will be starting on our chapter 3, which is to do with two-dimensional kinematics. Today is going to be part 1 of this chapter, and without further ado, let's begin. So the very first thing that we're going to start with are scalars versus vectors. Now, if you've watched my previous videos, you must have heard me going over scalars and vectors, and especially when we were talking about distance and displacement or speed or velocity, all those sort of things. And just to recap it, scalar has a magnitude only, whereas vectors has both a magnitude and a direction. But what does this term actually mean, right? And then more importantly, it means that it can be presented visually. So let's start with an example. Let's say that there is a car that is traveling 20 meters per second north, and then it travels 10 meters per second east to reach its destination. So now you've got these two conditions. So you've got a car that's traveling at 20 meters per second north, and then you've got it traveling at 10 meters per second east. That essentially means that you can represent this, and you can represent this as a sort of vector. So you've got a 20 meter per second north direction, then you've got a 10 meter per second east direction to reach its destination, right? So that's something that you can do with vectors, and that's a capability that you have with vectors only. If you were to do this with scalars, you won't be able to do it because it's got a magnitude. It doesn't point you in any direction or wherever that magnitude is acting, so to say, which when we come to it in our next chapter 4, it's going to become more prominent. So going to our next slide, what other things can we get out of this particular case? More importantly, can we find other details using the same example as before? So let's pull it back up. So we've got a car which is traveling 20 meters per second north and then 10 meters per second east to reach its destination. Well, can we do a little resultant plot to get to that part? Or is there another direction that the driver could have taken which could have been quicker or that sort of way? So remember your Pythagoras theorem, right? Or Pythagoras theorem. What that meant, or what that stated, was that it's if it is a right angle triangle, or if your journey can be broken down into a right angle triangle, then you can come up with a shorter journey, or a displacement in this case, which is given by this little white arrow right here, right, where this is represented by C, the opposite side is being represented by 10 meters per second, or A, and then the base is being represented right here is being represented by the 20 meters per second north case, because our right angle is stated right here. So let's try to find this resultant velocity. So if we start looking at this, I've labeled this as a resultant velocity. V is for velocity, so resultant is for resultant. So, and this is our Pythagoras theorem. What we can then do is, this is our formula. So again, we've got our hypotenuse right here, or C, and then we've got A as 10 meters per second right here, and B is equal to 20 meters per second. And that, if you equate it into this equation, we've got V resultant square is equal to V velocity in the east direction squared plus velocity in the north direction squared. And if you were to add it all up together, you're going to get 10 squared plus 20 squared equals to 100 plus 200, which equals to 500. Now, since this is a square on this side, you can take a square root on the other side for 500, and what you're going to end up with is about 22.36 meters per second, which is going to be your resultant velocity. Now, this is rounded off to 2 decimal points. And does this end up here? Not really. What we still need to do is, because we are talking about velocity here, we don't have a direction. We've only found a magnitude. We can label it as northeast because we were heading north, or the driver was heading north, and then the driver went east. you can say that the driver went northeast, but can we be a bit more specific? That's where our trigonometry comes in. So for trigonometry, what we're getting to is, let's start with our basic right angle triangle from the same equation. Right angle triangle means that one of your angles, so out of these three angles that are forming here, one of the triangles is going to be equal to 90 degrees. Now the sum of a triangle, or the sum of the interior angles of a triangle, is always equal to 180 degrees. What we can also label then are these lines, or the boundaries of the triangle. We've got one on the bottom, which is called the base. Then we've got a perpendicular side, and then we've got hypotenuse. A perpendicular, sometimes this is also known as a opposite. It's whatever you want to call it. I usually call it perpendicular because it's running perpendicular to the base. And then hypotenuse is the one that connects the opposite ends of the base and the perpendicular. Right? And then we've got another angle, which in this case I've drawn it next to hypotenuse and the base, which I've labeled it as theta. So what I can then start is, in order to find theta, one thing I can do is take sine theta, which is perpendicular over hypotenuse. I can do cos theta, which is base over hypotenuse. And then I can also do tan theta, which is perpendicular over base. Now, do you need to remember these things? You don't have to, but I would really recommend you do it. And essentially, there is one thing that you can do. The easiest way that I remember all of these equations, or these relations between sine, cos, and tan, and the lines of the triangle, or the boundaries of the triangle, is by memorizing the initials of each of these words. So S for sine, P for perpendicular, H for hypotenuse, C for cos, B for base, H for hypotenuse again, T for tan or tangent, P for perpendicular, and B for base. Right? And an even easier way that I've memorized it is by going through this little sentence, which is, some people have curly brown hair through proper brushing. Right, and that the first letter of each word in this sentence corresponds to, well, the first one goes to sine, the first three letters go to sine, the next three letters go to cos or cosine, and then the last three letters go to tan. Right, so we've got some people have, so sine theta is equal to perpendicular of hypotenuse. Curly brown hair, so cos theta over base is equal to base over hypotenuse, and then tan theta is, or through proper brushing means tan theta is equal to perpendicular or base. Now I'm using theta because I've used theta here. This could be any angle. It could be alpha, beta, phi, whatever Greek letters that are going to exist, or that the question has. But essentially you can have any combination of angles, and this is the way that I've memorized it. There are other methods like Secutor or whatnot. You can use those, but this is the one that has stuck with me through school. Right, so let's start with an example. Now let's say that this is our triangle that we came up with, so hypotenuse, perpendicular, base, 90 degrees, and theta. Well, can we apply this to our original equation, or our original problem where the driver was heading to find the direction? Right, so what we've got is that we've got a 20 meter per second velocity heading in the north, we've got 10 meter per second east, then we've got 90, and we've got theta angle, where the resultant velocity is ended up to be 22.36 meters per second. We roughly know what direction the driver was heading in, northeast, but we don't know what the exact angle was. Right, so what can we do? We can go back and let's start with sine theta. Sine theta is perpendicular over hypotenuse, right? So perpendicular over hypotenuse, and that's going to give you sine theta, and that was, in this case, this is our white line is hypotenuse, red one is our perpendicular, so it's going to be 10 over 22.36, which ends up to be 0.45. If we went with the cos theta route, that was cos theta is base over hypotenuse, so curly brown here, and then corresponding values on this little problem that we were discussing where that our base value is 20 meters per second, resultant velocity is 22.36 meters per second, which roughly ends up to be about 0.89 up to 2 decimal points when you round it off. And then moving on to tan theta. Tan theta is basically perpendicular over base, so through proper brushing, and that's 10 over 20. Our red color here is perpendicular, and then our green color here is base. So perpendicular over base is equal to 10 over 20 from these values, which is equal to half, or 0.5. Right? And then if you were to work these out, or if you were to calculate it using sine inverse or cos inverse or tan inverse, what you would end up with is going to be nearly 27 degrees. Now I've rounded these off to 27 degrees because if you look at these are round off errors that you get, and the round off errors you're getting are because I've actually rounded off all of these divisions to 2 decimal points. If you were to equate it, the entire calculation, whatever you get by dividing 10 by 22.36, if you were to take in sine inverse of that full value, you would get a better answer. Same goes here, so those answers would be comparable if you were to do the full values that you would get by dividing either 10 by 22.36 or 20 by 22.36, and then take either the sine inverse or cos inverse respectively. So what does this all mean though? Right, so reading position, what we've come up with so far is that this is the journey that the driver took. This is our resultant velocity, and after all these calculations, what we end up with is that theta is normal, almost 27 degrees. So the resultant velocity was that the driver took the driver drove about 22.36 meters per second, 27 degrees northeast. Right, that's one way to do it. So let's start with another example. And let's start by placing a compass where we've got our 4 cardinal directions. So we've got north pointing at towards the top at 0 degrees, and we've got east pointing towards the right of north at 90 degrees. Then we've got south pointing towards the bottom at 180 degrees, and then we've got west pointing towards the left of north at 270 degrees, and then we come back to north at 360 degrees. So we've completed a circle starting from north, going to east, then to south, then to west, then to north again. And then we've got an example that there's a cyclist who is moving or is cycling with a velocity of negative 15 kilometers per hour at a bearing of 240 degrees. And then the question states, how long will it take for the cyclist to cover a displacement of 100 kilometers in the eastward direction? Right, so there are a few things that are going on within this question. The very first thing is this term right here, bearing. What does bearing mean? Now, I don't know if you've done this before, or if this is in your vocabulary or not, but bearing is a way to tell which direction someone is moving in. And that definition is that bearing is an angular measurement of position, which starts in a clockwise direction. You start measuring it in a clockwise direction at 0 degrees from north, and then it is measured from that north direction wherever this is heading. So now this question is stating that the cyclist is heading at a bearing of 240 degrees. So 240 degrees would be somewhere around here, so 180 or somewhere around here. So I've got that. So we've got 240 degrees, and then it is pointing outwards that way. Now the velocity, on the other hand, is negative 15 kilometers per hour. That means that our cyclist is heading in this direction. Now, a really cool thing that you can do with vectors is that you can move the vectors. So I can essentially pick up this cyclist and I can point it or place the cyclist right here on the origin. So everything becomes quite easy for me to solve, rather than me going through and trying to solve what theta is going to be in terms of 90 degrees, subtracting 180 to get to this angle. What I can do quite simply is I can move the cyclist to this location, and it's perfectly fine. The solution is still going to be valid. And what has that done for me is that this has given me 30 degrees. Now, if I were to move the cyclist back here, what this allows me to do, I'm calculating that 30 degrees. So anything across this line is, or so the angle around here is going to be the angle when I move this vector around here, and that angle is going to come here. That 30 degrees is calculated simply 270 minus 240 degrees. This is equal to 30 degrees, and when I move this cyclist or this vector to this origin point, this angle is now come up here, and that's measuring 30 degrees. Now notice another thing, because I moved into this quadrant right here, my velocity direction's also changed. It's now become positive, and that's become positive to 15 kilometers per hour. So now what the question is asking us is, how long will it take for the cyclist to cover a displacement of 100 kilometers in the east direction? Right? Now remember, we're heading 15 kilometers per hour and at a bearing of, in this case, at a 60 degree bearing in the northeast direction, right? So it's your bearing is measured from our north axis, or our north location. Now, the very first thing that we need to do is we need to divide or distribute our velocity into its components. Into its components. So our x and y components, or in this case our north and east components. And then recall that we've got this little statement here that some people have curly brown hair through proper brushing, and that essentially means that you've got, for this little triangle right here, you've got sine theta, which is equal to perpendicular over hypotenuse. We've got cos theta, which is equal to base over hypotenuse, and then we've got tan theta, which is perpendicular over base. Right, so you can essentially use any of these functions, given that we know what theta is and we know what our hypotenuse velocity is in this case. We can then come up with, well, let's say that our V north is going to be 15 sine theta, if I'm using the sine function, which is equal to 7.5 kilometers per hour. Let's say, so sine theta is because I'm calculating this north one. My east velocity then is going to be the cos function, which is going to be 15 cos theta, and then which is going to become 12.99 kilometers per hour. Now the question was asking what is going to be, how long will it take for the cyclist to cover 100 kilometers in the east direction only, based on this vector. What you're going to get is simply, if you go back to our original displacement formula, speed displacement formula, delta t is equal to delta x over delta v, and that's going to be 100 over 12.99, or 100 kilometers divided by 12.99 kilometers per hour east is equal to 7.7 hours, or 7 hours 41 minutes and 54 seconds, however you want to write it. That's essentially your answer in this case. I hope this is making sense for all of you. I might be going a bit quicker on this, I'm not so sure, but this is what we're doing today. And to get to two-dimensional kinematics, is the concepts are the same from our previous chapter, which was doing with one-dimensional kinematics. We're just taking that one-dimensional knowledge and then applying it to a two-dimensional reference frame. So let's take this forward and let's move on to our previous example that I've used before. So if you recall that I've used this example, this picture right here that you see, which was used to help, or used to create, make you understand the concept of frame of reference, where I was measuring or trying to find what my displacement is from University of Dayton to CJ. Now what I'd done was I'd drawn this axis, and I talked about that I can measure my position or displacement from starting from this origin point to University of Dayton, and then to CJ, and then what my other displacement is going to be. Right now, I've also, this time what I've done is I've measured the displacement from my starting origin to CJ, which is shown in yellow, that is 1.15 miles. What I've also done is I've also measured the displacement from this origin point to University of Dayton, which is 1.02 miles, and then my displacement between University of Dayton and CJ was 1.22 miles. What I've also done this time is I've measured this displacement, which is the horizontal vector on the x-axis, so 0.98 miles. That measures 0.98 miles, and that's directly or vertically below the University of Dayton point. I've also done this for CJ from my origin point, which is measuring the displacement from this origin point vertically upwards, which measures 1.10 miles, and this is directly, or this point lies directly parallel to CJ. So what I can do with this part is then that I've got, going back to this original equation for a relation for sine theta, cos theta, tan theta, I can find these angles phi and theta, right, which have just popped up. And what that means is, for if I'm doing this displacement for University of Dayton from the starting point, that is going to be cos theta is equal to, because I've got two measurements, one's the hypotenuse and one's the base, so I've got base right here and hypotenuse. I can only take cos theta, and that's going to be 0.98 for the base divided by the hypotenuse, 1.02, because remember we're talking about right angle triangles, and since this point is lying vertically below the University of Dayton point, this is going to form a 90-degree angle here, right? So I can take that equation and I can do a cos inverse, and that's going to give me a 16.1 degree measurement for my theta angle. Similarly for CJ from my starting location, you've got a similar formula, because I know this is going to be the base in this case and this is the hypotenuse, because this is forming the right angle triangle. My angle phi in this case is going to be 16.96 degrees, right? Remember when I mentioned that you could have different angles in Greek, or different Greek letters for angles, and that's what we've done here. We've got theta, we've got phi. You can take alpha, beta, gamma, all of those can be used as angles. But that's one example that I wanted to come back to. This is to do with frames of reference, and you can then also, this also tells you that displacement, which has a direction, then can also be found from, if you know two displacement vectors, you can find what the resultant displacement is going to be from the origin point, or whichever point of reference that you're trying to measure the displacement from for that point. The next topic that we're going to talk about today is relative motion. But before I start, I must mention this. If that last part of the video is, you feel like that is enough for you, then that's fine. You can take a break here. You can continue working on your homework assignment. If you thought that you understood all of that content, then you can start with relative motion here, because this is only a couple of slides, and essentially you'll have today, and then when you come back on Monday, you can continue working on this. There will be a handout, not a handout, or an assignment that will be posted on Google Classroom, which you'll need to submit by 5 p.m. and it's going to be just an exercise based on two-dimensional vector breakdown, and then so you'll have some problems to do with those, and then some problems with relative motion. If you stop at this point, you can continue, and if you haven't understood, I would recommend that you go through and watch this video again, or if you just want to take a break, you can continue working on your homework assignment, and if you want to continue watching relative motion, please do so. So starting with relative motion, let's take two cars. We've got car A and car B. Now car A is heading towards the right direction and 60 miles per hour, whereas car B is traveling in the same direction at 75 miles per hour. Now this is a typical scenario that you've faced every day on interstate, right? What can be, so a good question could be, what is the relative velocity of car A to car B, right? So what is the relative velocity of car A to car B? So we're going to introduce a new formula here. So we've got velocity of car A relative to car B, and that's going to be VA minus VB, and then what you're applying in this case is that you've got 60 minus plus 75. So this is the formula, that doesn't change. So you've got 60, you're measuring the velocity of car A relative to car B. So what you're getting is 60 minus 75, and that's going to give you a negative 15 miles per hour. So car A is moving at 15 miles per hour slower than car B, or vice versa. Could be what is the relative velocity of car B, or what is the velocity of car B relative to car A, and that would be given as VB by A, and then you just flip these velocities and you would get 2 plus 15 miles per hour, where you're just essentially substituting the velocities into this original equation that we had put up here. And then the next part was what if we were going to flip this? So think about single lane roads where you're traveling. Let's take the same example. So car A is still traveling at 60 miles per hour, whereas car B is traveling at 75 miles per hour. Now, since we're coming back from the previous slide and our motion from left to right was taken as positive, what will happen in this case is if you were trying to find the relative velocity of car B to car A, or car B's velocity relative to car A, what would happen is, so you'll do VB by A, that's just a way to write what the relative velocity is. It's going to be negative 75 because it's heading in the opposite direction to our positive one, minus plus the 61 for our car A, and that's what you're going to get. So your total relative velocity of car B relative to car A is negative 135 miles per hour. And similarly, if you were to find the velocity of car A relative to car B, the signs are just flipped because we're working towards the positive direction. So it's going to be plus 60 minus negative 75 because car B is traveling in the opposite direction, and these minus and minus will change into a positive, and you'll get 135 miles per hour. And that's just a very brief intro of relative motion. We're not going to go more into it. This is just a concept introduction for relative motion. And this wraps up our today's lecture. Like I mentioned before, if you were able to complete this lecture up till now, that's great. And if you understood all the content, that's brilliant. Please take the remainder of the time to complete the homework assignment that was given to you yesterday. When you come in on Monday, if you understood all the course content, there's going to be an assignment that's going to be posted on Google Classroom, which is going to do with vector breakdowns and relative motion that you'll need to hand in by 5 p.m. on Monday. For today, this is all there is. This is the end of part 1 for chapter 3. There's another part to chapter 3 which is to do with projectile motion, but we will come to that after we're done with chapter 4, which is to do with forces, because then the description or the understanding of the projectile motion concept is quite easy. So that's it. Have a good day, have a good weekend. Thank you for paying attention, and bye-bye.